Picture our solar system. The sun takes center stage, planets twirl around it, but they all follow the rules. Well, almost all of them. There's one rebel in the bunch. It's Venus, the second planet from the sun. Venus doesn't play by the rules. It's the bad boy of our planetary family. Venus is a sight to behold. It shines bright in our night sky. Ancient cultures called it the morning star, or the evening star. They thought it was two different objects, but it's just one planet. Venus rotates backwards compared to most planets. It's like it's giving the finger to cosmic convention. Why does Venus spin the wrong way? What caused this planetary rebellion? These questions drive our curiosity about this strange world. Venus spins in the opposite direction to most planets. We call this retrograde rotation. It's like a ballerina spinning the wrong way in a dance. Most planets, including Earth, rotate from west to east. But Venus? It goes from east to west. It's a rebel without a cause. Or is there a cause we haven't figured out yet? Scientists have theories about Venus's backward spin. One idea is that Venus flipped over. Maybe a massive impact turned it upside down. Another theory suggests it slowed down and then reversed. The sun's gravity might have played a role. Or maybe it's been spinning this way since birth. The truth is, we're not sure. Venus's day is longer than its year. A Venusian day lasts about 243 Earth days, but it only takes 225 Earth days to go around the sun. Imagine a year passing before a single day ends. This slow rotation has consequences. It affects Venus's magnetic field. This leaves its atmosphere exposed to the sun's fury. At first glance, Venus and Earth seem like siblings. They're nearly the same size. Venus is just slightly smaller. They have similar mass and density. Both are rocky planets with cores of iron. They orbit in the sun's habitable zone. This zone is where liquid water could exist on a planet's surface. But that's where the family resemblance ends. Earth is the blue planet, teeming with life. Venus is a scorched hellscape. Earth has oceans, rivers, and rain. Venus has plains of bare rock and lava flows. Earth's sky is blue, filled with oxygen and nitrogen. Venus's is a perpetual orange haze of carbon dioxide and sulfuric acid. The differences go beyond the surface. Earth's magnetic field protects us from solar radiation. Venus has no such shield. Our planet has plate tectonics, constantly reshaping the surface. Venus might have once had this, but not anymore. Despite these differences, studying Venus is crucial. It helps us understand Earth better. By studying Venus, we learn more about climate change on Earth. Venus's atmosphere is a beast. It's mostly carbon dioxide, creating a runaway greenhouse effect. The surface temperature is hot enough to melt lead. It averages 462 degrees Celsius. That's hotter than Mercury, despite being further from the sun. The atmosphere is so thick it would crush you. The pressure at the surface is 90 times that of Earth at sea level. It's like being 900 meters underwater. The clouds on Venus are nothing like Earth's. They're made of sulfuric acid. They're so thick and reflective that they hide the surface from view. These clouds create a perpetual orange haze. They trap heat, making the greenhouse effect even worse. It rains sulfuric acid on Venus, but it's so hot that the rain evaporates before reaching the surface. The surface of Venus is a barren wasteland. It's covered in volcanic plains and impact craters. There are two continent-like highlands. They're called Ishtar Terra and Aphrodite Terra. Mountains dot the landscape, including Maxwell Montes. This mountain is taller than Mount Everest. Venus might have once had oceans, but they boiled away long ago. The lack of water makes the planet even hotter. Venus isn't the only planet with a weird spin. Uranus is tilted on its side. Its axis is tilted 98 degrees relative to its orbit. This means it rolls around the sun like a ball. Its poles take turns facing the sun directly. Imagine seasons where the sun doesn't set for 42 years. Then it's dark for another 42 years. Mercury has a peculiar rotation too. It spins 3 times for every 2 orbits of the sun. This 3-to-2 resonance is unique in our solar system. It means that a solar day on Mercury, from one sunrise to the next, lasts 2 Mercury years. Jupiter, the king of planets, is a speed demon. It completes a rotation in just under 10 hours. That's the fastest of any planet in our solar system. This rapid spin causes the planet to bulge at its equator. Jupiter isn't a perfect sphere. It's noticeably wider than it is tall. Pluto, though no longer considered a planet, has its own rotational quirks. It's tilted at 122 degrees, even more extreme than Uranus. Its largest moon, Charon, is tidally locked to Pluto. They always show the same face to each other. Tidal locking is a cosmic dance. It happens when a body's orbital period matches its rotational period. The moon is tidally locked to Earth. That's why we always see the same side of the moon. The far side remained a mystery until space exploration. Tidal locking is common for moons orbiting planets, but it can happen between planets and stars too. How does tidal locking work? It's all about gravity. The larger body exerts a stronger pull on the near side of the smaller body. This creates a bulge. Over time, this bulge acts like a brake. It slows the rotation until it matches the orbital period. The moon isn't the only tidally locked body in our solar system. Many of Jupiter's and Saturn's moons are tidally locked. Pluto and Charon are mutually tidally locked. They always show the same face to each other. Some exoplanets are thought to be tidally locked to their stars. This could create planets with one side in perpetual day and the other in eternal night. Tidal locking has significant effects on a body. The locked side facing the primary body gets heated more. The far side stays cooler. Our solar system began as a vast cloud of gas and dust. About 4.6 billion years ago, something disturbed this cloud. Maybe it was a passing star or a shock wave from a supernova. Whatever the cause, it started a collapse. The cloud began to spin and flatten into a disk. Most of the material gathered at the center, forming the sun. The rest of the disk became the planets, moons, asteroids, and comets. As the disk spun, it broke up into rings. These rings were at different distances from the forming sun. Closer to the sun, only rocky materials could survive the heat. This is where the inner planets formed. Further out, it was cool enough for ices to condense. This region gave birth to the gas giants. The leftover debris became asteroids and comets. It was a messy process full of collisions and chaos. The planets didn't form in neat, orderly ways. They grew through countless collisions. Smaller bodies smashed together, forming larger ones. The final arrangement of planets is the result of this cosmic pinball game. It's amazing that any kind of order emerged from this chaos. The rotation of planets is a complex topic. It's not just about how fast they spin. The direction and tilt matter too. These characteristics are influenced by many factors. The initial rotation comes from the angular momentum of the forming planet. But that's just the beginning. Impacts can change a planet's spin dramatically. A big enough collision could even flip a planet over. The sun's gravity plays a role too. It can slow down a planet's rotation over time. This is especially true for planets close to the sun. Mercury and Venus have slowed considerably since their formation. The presence of large moons can also affect rotation. Earth's moon helps stabilize our planet's tilt. Without it, Earth's axis would wobble chaotically. This would cause extreme climate shifts. Planetary rotations aren't set in stone. They can change over time. Tidal forces can slow a planet down. The Earth's rotation is slowing by about 1.8 milliseconds per century. It doesn't sound like much, but it adds up over billions of years. Venus remains one of the most enigmatic planets in our solar system. Its thick atmosphere hides its surface from view. This makes it challenging to study. We've sent probes to Venus, but they don't last long in the harsh conditions. The Soviet Venera missions provided our only images from the surface. They lasted mere hours before succumbing to the heat and pressure. One of the biggest mysteries is Venus's lack of a magnetic field. Earth's magnetic field protects us from solar radiation. It's generated by our planet's liquid metal core. Venus is similar in size and composition to Earth, so why doesn't it have a magnetic field? Is its core solid, or is the slow rotation to blame? Another puzzle is the superrotation of Venus's atmosphere. The upper atmosphere spins much faster than the planet itself. It completes a rotation in just 4 Earth days. We don't fully understand what drives this phenomenon. Exploring Venus is a daunting challenge. The extreme conditions make it hard for spacecraft to survive, but that hasn't stopped us from trying. NASA's Magellan mission mapped Venus's surface using radar. The European Space Agency's Venus Express studied its atmosphere. These missions have given us valuable data, but there's still so much we don't know. Future missions to Venus are in the works. NASA has approved 2 new missions, Da Vinci Plus and Veritas. Da Vinci Plus will plunge through Venus's atmosphere, measuring its composition. Veritas will map Venus's surface in high resolution. These missions could revolutionize our understanding of Venus. They might help us solve some of the planet's long-standing mysteries. Some scientists dream of more ambitious Venus missions. What if we could land a long-lasting probe on the surface, or float an airship in the upper atmosphere? The upper atmosphere of Venus is almost Earth-like in temperature and pressure. It might be the easiest place to explore. Exploring Venus isn't just about understanding one planet, it's about understanding planetary evolution. Every bit of knowledge we gain,